Hello, let's talk a little bit about the constructions and validations studies on principal prototype of electric fault filling simulation system. So we all know the electric fault filling system is the in development in the simulation system, in the simulation platform. And the key idea is to improve the control loading fidelities of helicopter flight simulations, fault filling simulation systems, to develop the principal prototype of fault filling simulation system by establish the electromotive force servo loading system model, applies the model to the fault filling simulation system principal prototype, and to conduct the test of sense of force, and to show that the design of it is reasonable. Using the model of force temporal tracking and force displacement trajectory tracking to study the sense of force tracking performance. And it can be shown that the algorithms such as the conventional PID control is hard to satisfy the real-time accurate tracking for model of force. To improve the tracking speed and precisions, it needs some feed-forward compensations with PID and feed-forward iterative learning control strategy should be used. Let's look at some introduction. From the previous work, force filling simulation system is an important part of flight simulator, which can be used for the simulations of the interactive like joystick force and paddle force of pilot driving in the aircraft simulator. The performance of fault filling simulations directly affect the realistic level and quality evaluations of flight simulator. In order to excellently develop it, the fault filling simulation, it needs development of the principal prototype of fault filling simulation system first. Rotation like rational design for the prototype directly determines the overall control performance and the sense of force fidelity of fault filling simulation system based on the overall indicators of helicopter flight simulator electronics or electric fault filling simulations. It is to design the hardware and software system for the prototype by using the reasonable control strategy and select the optimal control parameters. Simulate and verify the principle of the prototype, applies the actual flight simulator fault filling simulation system, and improve the fault filling simulation system fidelity. Let's look at the hardware system from the mechanical structure design. The overall mechanical structure is the hardware implementation platform for the electric fault filling simulation system, mainly used for installations of seat mechanisms, driving mechanisms, and fault servo actuator and sensors measuring element. Overall structure should meet the demand of indicators. The design of mechanical structure should follow the following point First, the size of the real machine cockpit layout should confirm the body's normal operator habit. Secondly, the system should be loaded by a high precise force servo motor, transmitter, mechanisms, and minimize the mechanical connections which connect the mechanism in order to reduce frictions and inference of lag mass initiator. The design of control cabinet should be rational distribution. Avoid electromagnetic interface between each channel communication lines. Finally, maintainability and disassembly of mechanical structure should be ensured, make it easy maintenance, a long service life. To summarize, the computer-aided design, sometimes like CATIA, could be used to design the mechanical structure diagram for experimental prototype, for rational design of prototype system structure, and parameters to accurate calculation of driving stick to electric cylinders output ratio, the paddle, and the output transmission ratio of electric cylinder, and the layout of seat. For the control system design, the principal prototype of electric force servo control system, which was studied in previous works, is composed of torque motor, increment photoelectric encoder, such as 12-bit resolutions, electric cylinder drive, a data acquisition card, force sensor, human sense simulation computer. For example, specify parameters as the human sense simulator computer. This is the human sense simulator computer with some dual-core processors produced by Ewok Company with 2.5 GHz HPC 6022 industrial integrated workstations as the CPU clock. And the second would be the DAQ or D2A converter card. D2A converter card is 6 channels, 16-bit PCLD X710 card produced by Yanhua Company. The output length from -10 to +10 volt, and the accuracy is about 0.05 millivolt. Third would be torque motor. The torque motor is permanent magnet synchronous motor with pole magnet surface, silent pole magnet surface type, produced by the Naibo Fieschi Company. The pole number is 3. The maximum stall torque is for multiply 10 power 5 Newton meter, or is about 400,000 Newton meter, and the rate speed is about 9,000 round per minute. The angular position feedback is incremental photoelectric encoder with accuracy of 0.005 degree. Next would be the force sensor. The force sensor is S-type strain gauge torque sense produced by American Transcell Company with read length of 250 kilogram, resolutions of 0.05 percentage, and accuracies of 0.001%. Next would be the programmable drive. The model drive is current vector control motion controller produced by Germany's Leglos company with a rated power of 4.5 kilowatt, supplied by 380 voltage, industrial AC power. Next is data acquisitions. This is the data system is CIFX data acquisition card produced by Hewlett company. It transmits data to the computer serial port with SIRCOD 3 prototype communication mode. In addition, in order to improve the anti-interference ability of the system in the hardware design focuses on filtering and shielding problem. Because of high frequencies, the force sensor feedback system is in differential amplifications transmission. It is effectively to improve the system anti-interference by using high-quality shield cable for the signal communication, a low-frequency filter for 3-phase high-power input and output. And next would be the software subsystem design, where we grab information from the previous work. The software subsystem design of electric fault filling simulation system is mainly to complete the force solver for 4-channel mode to realize the control strategy, data visualization, and data communications, and other tasks. In order to improve the real-time and synchronizations, the fault filling simulation software platform were designed, which was based on Windows XP and RTX. Data display and visualization work complete by Windows XP. The control strategies and various compensation tasks complete RxD real-time operation system. The ideas of the software consist of 3 part, such as a constructions of real-time system, which we grabbed information from the work. Electric force filling simulation system computer task, which is a computer task. It is an industrial control PC computer as a platform of the software and hardware. The real-time of the Windows operation system does not meet the strong real-time requirements for the system in US. We call Ardent Company, which launched the RTs based on real-time extensions for Windows subsystem and modify and extend hardware abstraction layer for the system with 220x levels of priority. So this system is suitable for industrial process real-time control. So that is summarized of the real-time system, RTX. The RTX in this work is a real-time extension subsystem and PC combined with industrial motion control card realize the strong real-time control task. And there is no universal software package to achieve the industrial control. it strong need to develop their own set of software system, including the driver. The control interface of electric force field simulation system could be shown in the window with XP. To realize the control mode set and output and display of control interface data to the RTSS process, which belong to the RTX subsystem, to realize force calculation of model, control algorithms, data acquisitions, and data communication tasks in the real-time operation system of force field simulation system. It gets strong real-time multitask process by sharing memory of Windows XP and RTX. Let's go back to the system software process design. Systems process design consists of the software system process control, which the electric force field simulation system is initially in standby stage. Is switched work stage when receiving the initialization command. If the failure occurs during initializations, the work stage will turn into full processing. Then the system reset and enters in the standby stage and start work again. If the system initialization is normal, then it enters the work stage and realizes the sense of force simulations of the control system, accepts the control command at the end of the test, then enters the standby stage. And then go to number 2, the software process of longitudinal channel. When the human sends simulation computer of electric force field simulation system works simultaneously, it solves the model force of the 4 channels of the aircraft. So in order to taking a helicopter simulator longitudinal single channels as an example, we design a subroutine flow diagram of each channel. So after the startup and initialization of the system, the motor will drive the driving stick back to median uniform in position mode. Then conduct 4 kinds of mode identification. Take longitudinal channel as example. When the external force acts on the driving stick, the system will select artificial manipulation mode, and entry into force closed loop mode. Otherwise, to enter the 3 kinds of mode for safety considerations for personnel and system, set the maximum speed difference, position difference, and for different module. The system automatically turns off since it exceeds the threshold value. So it's for safety considerations. Then, in the last mode, the model force solvers module design, with got information from the reference. Model force solver calculate in RTSS process, which is the extension subsystem of RTX. Then from a control variables output to drive interface. After comparisons with actual output, take the longitudinal channel module force solver as example, and based on longitudinal stick force model of force field simulation system, calculates the real-time model force by receiving parameters of mass to computer, stick relative displacement, the output displacement of the encoder, and the speed command, for example. And then go to the diagram. The system validation studies. So to verify the sense of power tracking performance of electric force field simulation system, it is important to develop the principal prototype trial and errors, or trial and trial, and to do test tracking performance of the force sense. The study contains the actual output of the system by conventional PID control with feed-forward compensation, with PID control and some feed-forward in iterative learning control. So it's a different kind of control. Specified verification method are the model force time domain tracking, tracking stick force displacement trajectory tagging, and the experimental validated studies conducted on conventional PID control. In the electric force servo loading model, according to the AC servo motor performance index, we choose the electric cylinder. And let the Baozi drive as kg unit, as meter per radian, and set F as motor output angle. The Baozi of elongations is L. The force sensor is the key component to connect the motor with load object. Because it's small inertia and friction, it can be regarded as proportional component and simple force model. And in some formula, there is coefficients of the force sensors and angle of difference across the sensor deformations and the output disturbance force. To build the servo loading system based on mathematical model of the above thing that we said, the outer ring of electric force servo loading system is a closed loop feedback in order to realize the force closed loop control of control loading system, and at the same time ensure the steady precisions and dynamics tracking performance, and get the block diagram loading as in this picture. And according to this, we get the forward channel closed loop transfer can be put in equation, which is the main thing like C, like GF, main feedback control transfer functions, GPI, speed loop controller transfer functions, GIQ, and the current loop controller transfer functions. And in the experiment, it has the experiment of the conventional PID control on the complete principal prototype based on electric force servo loading system. After repeat experiments, the system get exceed force interference along with the control stick movement in dynamic loading process. After repeated adjustment of control parameters and without any compensation measures, we get the optimal control results, which show in this picture. It has, on the top is the curve of a stick speed output curve of the system. In the upper there is a different line, isn't it? It have three lines, three curves. Number one is a stick speed output curve of the system. So it's the speed. And number two is the green one, is the stick force output, which is the number two. And number three is the force curve of the model. And number three is a red line, is the force from the model. And the bottom picture, this is the curve number one and number two. Number one is in the blue line and number two is in the red line. It stands for the model force and actual output stick force. So there are some model and the actual output. It can be seen from this picture. In the top, there exists a lack excess force interference in the system, making the shock phenomena of the system output, as in the peak, especially in the process of pushing the stick to the limit position, putting the stick to the limit positions. So the shock phenomenon is more serious. The maximum error exceeds the maximum output 50% at the same time. The actual output tracking force phase has lagged far behind the model force. So it has lagged far behind the model force. And the sense of the force simulation system tracking performance of electric force field simulations is difficult to guarantee. So in the lower picture, the output curve of longitudinal channel stick force displacement is significantly distorted. The entire process of the stick from the neutral position back to neutral position at the last. At the start point and the termination point, the model force equal to the output force, while in the other process, the output force seriously lag behind the model force. In addition, the stick force output curve in this picture, it can be seen that the process of moving steering stick force transmissions is fluctuations, and the smoothness of the stick force cannot be guaranteed. By analyzing the data, the shock is mainly caused by input of differential term because of small sampling period and communication on a lock-stock manipulations in manipulation stick. The output force changes largely in the unit time, which is greater than 500,000 Newton per second and has a longer differential. However, the differential coefficient is really small. The steering stick has no derivative actions in low speed ring of travel and increase some phenomena like hysteresis or hysteretic quality of output stick force. So in some conclusions, there's the results of simulation and test show a desired principal prototype is reasonable. The sense of force tracking performance of the electric force field simulation system can be researched through the time domain tracking of modal force and trajectory tracking of the stick force displacement. At the same time, the control algorithm studies also show that the conventional PID control method is difficult to meet the requirement of real-time accurate tracking of modal force. In order to improve the speed and precision of tracking system, the controller should add feed-forward compensation and PID control and feed-forward interactive learning control. Thank you.